Welcome to the deep dive. Today, we are exploring a concept that Albert Einstein famously called spooky action at a distance. And while he absolutely hated it, our title today is Einstein's Nightmare is Becoming Technology.
Yeah, it's a pretty bold title, but when you look at the three new Nature papers we are diving into, you realize we are actually crossing a massive threshold here. I mean, we are watching a bizarre theoretical puzzle become a practical engineering resource.
Okay, let's unpack this because if you are listening to this, you are about to get a serious shortcut to being incredibly well informed on the absolute cutting edge of quantum physics. And we're going to do it without making you suffer through impenetrable whiteboards of math.
Right, no math equations today, I promise.
Thank you. But before we look at the new tech, we kind of need to talk about Einstein. You hear people say he was foolish to doubt entanglement.
Which is completely unfair. I mean, he wasn't foolish at all. His objections were rigorous and honestly brilliant. Einstein believed in locality, which is, the intuitive idea that things can only be influenced by their immediate surroundings.
Right, like if you drop a coffee mug, it falls and shatters right there. A magnet only pulls things that are close to it.
Exactly. But quantum entanglement suggested that two particles could be linked so deeply that measuring one instantly dictates the state of the other, even if they are light years apart. To Einstein, that meant reality was fundamentally non-local.
And he rejected that entirely. He basically said, the universe cannot possibly be that spooky. But nearly 90 years later, these three papers show us finding that spookiness, sending it, and actually using it.
Yeah, it's pretty incredible.
So let's start with finding it, because if we are going to build technology out of a physical phenomenon, we have to prove it survives outside of, pristine, ultra-cold laboratories, right?
Precisely. We need to know if entanglement can survive extreme, chaotic conditions in nature. And that brings us to the first paper, which comes out of Geneva, Switzerland, deep underground at CERN's Large Hadron Collider.
The biggest, most complex machine ever built by humans. And they're smashing protons together at immense, frankly terrifying energies. We're talking 13 tera-electron volts.
Yeah, to put that in perspective for you, they are essentially recreating conditions that haven't existed since fractions of a second after the Big Bang. And in these unimaginably violent collisions, they briefly create the heaviest known fundamental particles in the universe.
The top quarks and antiquarks.
Right, top quarks.
Now, in the papers, the lifespan of a top quark is listed as roughly 10 to the power of negative 25 seconds. That's a decimal point. 24 zeros and a 1.
I mean, I can't even conceptualize a slice of time that microscopic.
It is absurdly short. But that brevity is exactly why the top quark is the perfect test subject for entanglement. Normally, when you smash particles and create quarks, they instantly interact with the strong nuclear force.
They grab onto other nearby quarks, right?
Yeah, they bundle up into larger particles in a process called hadronization.
It's like they instantly put on a disguise. And when they get cloaked like that, their fundamental quantum information just gets scrambled by the strong force. Exactly. But the top quark decays so incredibly fast that it literally doesn't have time to hadronize. It dies before the strong force can even reach out and scramble its data.
I love looking at this like a quantum crime scene. You have these two suspects, the top quark and the antiquark, born from this massive collision, and they are perfectly entangled.
Right, from the very start.
But they vanish long before the investigators, which in this case is the massive ATLS detector at CERN, can actually arrive on the scene to see them.
But they leave clues behind. When they die, they decay into other particles, specifically charged leptons.
Right.
And because the top quarks bypass that scrambling process we talked about, their core quantum identity, specifically their spin information, is perfectly preserved in the trajectories of those charged leptons flying away from the crash.
Okay, wait, stop there for a second. Spin in quantum mechanics doesn't mean the particle is physically spinning like a tiny toy top, does it?
No, not at all. It's a measure of intrinsic angular momentum. It's a very abstract mathematical property.
Got it.
But the crucial part is that if the original quarks were entangled, the angles at which their decay products fly away will be mathematically correlated in a way that classical physics says is strictly impossible.
And the ATLA's collaboration proved this. They sifted through mountains of collision data, looking at the angles of these charged leptons. They used an entanglement marker called D.
Yeah, the D marker.
Now, the threshold to prove entanglement is negative 1/3. But the ATLA's team reported a measurement of negative 0.537. Why is negative 1/3 the magic number here?
It all goes back to something called Bell inequalities.
Oh.
So without getting lost in the math, imagine a limit to how well-coordinated two classical objects can be without secretly communicating.
Like a natural speed limit for coordination.
Exactly. Negative one-third is that absolute mathematical limit. If you measure a correlation stronger than that, like negative 0.537, you have mathematically proven that the particles share a single quantum state. I mean, there's just no classical explanation.
And they achieved a statistical significance of greater than 5 standard deviations, which I know is the gold standard in physics for a definitive, undeniable discovery.
It absolutely is.
But step back for a second. What does this actually mean for you and me? Why does it matter that two particles nobody has ever seen are entangled for a fraction of a second in a tunnel in Switzerland?
Well, it matters because this is the highest energy observation of entanglement ever recorded, and the first time it's been seen in a pair of quarks.
Oh, wow.
Yeah. It fundamentally proves that entanglement is not just some delicate anomaly that only happens when scientists carefully coddle atoms in a vacuum. It survives the most violent explosions in the universe. It is deeply woven into the very fabric of reality.
So the universe is inherently spooky at its core, even when things are exploding at the speed of light, which is mind-blowing. But, it leads us directly to the problem in the second paper.
The engineering problem.
Exactly, because if entanglement only survives for 10 to the power of negative 25 seconds inside a multi-billion-dollar particle accelerator, we can't build a computer out of it. We can't use it for an internet.
Right, it's completely useless for infrastructure.
We need to catch it, keep it alive, and move it across a city. How do we take something that fragile and put it into an optical fiber?
That is the exact challenge the Harvard team tackled in our second Nature paper. We are leaving the fundamental physics of CERN and moving into the practical urban engineering of Boston, Massachusetts.
They set out to build the foundational hardware for a quantum network.
Yes, and this is where they used silicon vacancy centers in nanophotonic diamond cavities.
Okay, you just lost me again. That sounds like Star Trek jargon meant to fix the warp drive. What does that actually mean for the hardware? Like, why diamonds?
It's not as sci-fi as it sounds, but it is brilliant engineering. A diamond is just a very rigid lattice of carbon atoms.
Right.
Now imagine a microscopic flaw in that lattice, where one silicon atom sits between two missing carbon atoms.
So an intentional impurity.
Exactly. That flaw, the silicon vacancy center, is essentially an artificial atom trapped inside the diamond. The diamond acts like a perfect, rigid cage that protects the delicate quantum state from heat and environmental noise.
Okay, so inside this tiny diamond cage, what is actually doing the work?
You have three key players. First, the electron spins. These are the quantum communicators. They are highly interactive and really good at absorbing and emitting light.
Okay, that's one.
Second, you have the nuclear spins. These act as the memory.
And the paper notes they can store quantum information for up to an entire second, which, in quantum terms, might as well be an eternity, right?
Oh, a full second of coherence is incredibly long.
Yeah.
It gives you ample time to actually process the data. So you have the electron talking, the nucleus remembering, and the third player is the photon.
The photon is the flying messenger that carries the entanglement from one diamond node to another across a fiber optic cable. But there is a catch. The photons generated by these diamond communicators are emitted at 737 nanometers. That's visible red light. And let me guess, standard telecom fiber optics do not play nicely with visible red light.
It's an absolute nightmare for telecommunications. If you try to send a 737 nanometer photon down the standard glass fiber that currently runs our internet, the glass absorbs it almost instantly. The signal dies within meters.
So they need a different wavelength. Now, in my notes, I originally thought this was like an analog to digital translation, like taking a delicate whisper and turning it into a standard digital phone signal. But that's completely wrong, isn't it?
Yes, very wrong. Because if you digitize or copy a quantum state, you destroy the entanglement.
Oh, right. Because of the no cloning theorem?
Spot on. The laws of quantum mechanics strictly forbid you from cloning an unknown quantum state. If you copy it, you kill it. So they couldn't digitize it.
So what did they do?
They had to change the photon's frequency while perfectly preserving its fragile quantum identity. They used a process called nonlinear optical frequency conversion.
Okay, explain that like I'm 5. How do you change a photon without touching its quantum data?
Imagine sending your delicate red photon into a specially engineered crystal. Inside this crystal, you fire a very specific, powerful pump laser.
Okay.
The crystal allows the red photon to essentially borrow energy from the laser, perfectly stretching its wavelengths from 737 nanometers to 1350 nanometers.
And 1350 nanometers is what they call the telecommunications O-band.
Exactly. It's the infrared frequency. Our current global internet infrastructure is already designed to carry with almost zero loss.
Wow. So the photon exits the crystal carrying the exact same spooky quantum connection, but now it's wearing a disguise that lets it slide perfectly through standard glass fiber.
Exactly, a perfect disguise.
And here's the part that I find so incredibly poetic.
Yep.
They didn't do this in a sterile vacuum tube on a lab bench. They routed this entangled signal through a 35-kilometer loop of deployed commercial telecom fiber running right under the streets of the Boston area.
Real-world infrastructure.
Yes. Above ground, you have people drinking coffee, riding the T, honking their horns in traffic, totally oblivious. And beneath their feet, inside dirty, practical city infrastructure, fragile quantum correlations are zipping back and forth, successfully entangling two distinct nuclear memories.
It perfectly illustrates the shift from theory to infrastructure. Now, we should be very clear here for you. This isn't a fully functioning quantum internet that you can plug your phone into tomorrow.
Right. We aren't streaming movies on quantum entanglement just yet.
No, definitely not. But they have solved the hardest hardware problem for what we call quantum repeaters.
What's a repeater do?
Well, classical internet signals degrade over distance, so we use repeaters to copy and boost the signal. But since you can't copy quantum signals, a quantum repeater has to catch the entanglement, store it in memory, and stretch it further down the line.
Ah, I see.
By proving they can store it in diamond memory for a second, cleanly shift its frequency, and send it under a city, they've proven the hardware for a global, unhackable quantum network is entirely possible.
Okay, I want to push back a bit here, though. I get that it's incredibly cool that we can send spooky action through dirty Boston telecom pipes. But what is the actual ROI here? Why are researchers spending millions of dollars just to prove they can entangle two microscopic diamond flaws across a city? What is the technological payoff of distributing this?
The payoff is fixing the biggest bottleneck in quantum computing today. And that brings us to our third paper out of Oxford University.
The USEIT phase.
Right, because right now, building one gigantic monolithic quantum computer with millions of qubits, all perfectly isolated in one box, is proving prohibitively difficult.
Because of the cooling requirements, right? The papers mentioned dilution refrigerators. What exactly is a dilution refrigerator?
It is a massive, highly complex, multi-million-dollar freezer that cools quantum chips down to temperatures colder than deep space.
Wow.
We're talking just a fraction of a degree above absolute zero. You need that extreme cold to stop thermal noise from destroying the qubits. But, you can only build a fridge so big.
Right, there are physical limits.
Exactly.
Yeah.
You can only run so many wires inside before the heat from the wires themselves ruins the environment.
So you literally run out of physical space to scale up the brain of the computer.
Precisely. So the researchers are asking, what if we don't build one giant brain? What if we build smaller, highly efficient quantum modules in separate freezers and link them together so perfectly that they behave as one single massive machine?
Distributed quantum computing.
Exactly. And that is exactly what the Oxford team achieved.
So they set up two distinct trapped ion modules, let's call them Alice and Bob, and they are sitting in the same lab about 2 meters apart from each other. Now, 2 meters might as well be 2 light years in the quantum realm if they aren't physically touching.
Oh, absolutely. Inside Alice and Bob, they are trapping individual ions using electromagnetic fields in a perfect vacuum. And each module holds two types of ions.
Okay, why two?
They have a strontium ion, which acts as the network interface to talk to the outside world. And they have a calcium ion, which acts as the memory and the logic gate. The calcium is the mathematician doing the actual computing.
So first, Alice and Bob use their strontium ions to fire photons at each other, establishing a link of entanglement across that 2-meter gap, just like they did in the Boston fiber.
Right. Now they share an invisible bridge.
But here's the crux of the whole thing. How do you use that shared entanglement to make the calcium ion in Alice perform a logic operation with the calcium ion in Bob without ever moving the ions?
You have to use a process called quantum gate teleportation.
Okay, I have to jump in right there to prevent a sci-fi misunderstanding, because I know what happens when people hear the word teleportation.
They picture Star Trek.
Exactly. They picture matter dissolving in one tube and materializing in another, or they picture faster than light communication. I need to be completely clear with you listening. They are not teleporting physical atoms, and they are not sending messages faster than light.
That is a very crucial distinction. What they are teleporting is the logic state. They are teleporting the mathematical operation, the gate itself, across the gap.
In previous drafts of my notes, I used a puzzle piece metaphor here, but I realized it doesn't really explain how teleportation works at all. Can we break down the mechanism of teleporting logic?
Sure, let's use the analogy of two locked boxes. Imagine Alice has a box containing her computational state, and Bob has his box 2 meters away. Because of that initial strontium-photon exchange we talked about, their boxes share a mathematical link, like a pre-shared quantum key.
Okay, I'm with you.
If Alice wants to perform a joint operation with Bob, she doesn't send her state to him. Instead, she performs a measurement on her box and her half of the shared key simultaneously.
And by the rules of quantum mechanics, the act of measuring her state destroys it in her lab, right?
Yes,
Yeah.
it does.
Yeah.
But because of the entanglement, destroying it in her lab instantly forces Bob's box into a highly specific mathematical state.
So it changes Bob's box immediately.
Yes. Then Alice picks up a classical phone line, calls Bob, and says, "Hey, I got measurement result X." Bob uses that classical information to apply a minor tweak to his box, and suddenly his box contains the exact, perfectly executed logic operation they wanted to achieve together.
The computational logic literally leaps across the room.
Exactly.
That is staggering. To get specific, the paper says they teleported a controlled Z gate, or a CZ gate.
Which is a fundamental two-qubit operation. Simply put, it's an operation where the state of one qubit conditionally changes the mathematical sign called a phase flip of the other.
It is a core building block of quantum logic, and they achieved this teleported gate between Alice and Bob with an 86% fidelity.
Meaning 86% of the time, this incredibly complex, non-local, teleported logic operation worked exactly as a perfect localized computer would.
But they didn't just prove the gate worked once and call it a day. They actually used this distributed setup to run a real algorithm. They executed Grover's search algorithm.
Right. Grover's algorithm is a famous quantum algorithm used for searching through unsorted data exponentially faster than a classical computer could ever do.
Like trying to find one specific name in a massive phone book that hasn't been alphabetized.
A total nightmare. Classically, you have to read every single name one by one until you hit it. But Grover's algorithm allows a quantum computer to evaluate multiple possibilities simultaneously and just amplify the correct answer, finding it almost immediately.
And the Oxford team ran this search algorithm across the two completely separate modules, Alice and Bob, using teleported gates, and achieved a 71% success rate.
Which is huge.
And the paper uses the word deterministic, which is vital here. It didn't just happen by random chance or by running the experiment a million times and throwing away 99% of the failed data until they found one that worked. They commanded the distributed algorithm to happen, and it worked on cue.
It is an absolute milestone. They have proven that we can essentially stitch separate, isolated quantum processors together into a much larger, infinitely scalable quantum fabric. You don't need a single dilution refrigerator the size of a skyscraper. You can just network smaller ones together using entanglement.
Okay, we have covered an immense amount of ground today. Let's bring this all together for you. We started by finding it. We went to CERN, looked at the incredibly brief lives of top quarks in 13 TeV collisions, and proved that entanglement isn't just a fragile lab trick, it is a violent, fundamental property of the universe.
Then we explored sending IT. We went to Boston, took that fundamental property, and showed how human engineering can store it in diamond memory, translate its frequency, and shoot it through 35 kilometers of dirty, real-world telecom fiber beneath a bustling city.
And finally, we looked at using IT. We linked Alice and Bob, two separate trapped ion processors, and used that shared entanglement bridge to literally teleport logic gates and run actual computing algorithms across a physical gap.
Which really brings us back to Einstein and the central question of all this research. What happens when one of the strangest, most perplexing properties of reality stops being a mystery and starts becoming infrastructure?
It changes the entire technological paradigm. It means a future of totally unhackable communication networks and infinitely scalable distributed quantum computers isn't just theoretical physics being debated on chalkboards anymore.
No, it's a tangible engineering problem.
And as these three Nature papers emphatically show, it is an engineering problem that is being solved right now, piece by piece, under our feet.
I want to leave you with a final thought to mull over. We have just spent this deep dive talking about how human engineering can now successfully entangle and synchronize completely isolated systems across vast physical distances using the very fabric of nature. But if we can do this with lasers, diamonds, and telecom fiber. What other seemingly isolated systems in our universe might already be secretly communicating through natural entanglement on cosmic scales? What if the universe is already fundamentally networked, and we simply haven't learned how to read signals yet?
Now that is a thought that would have kept Einstein up all night. If you enjoyed this story, please like the video and subscribe to the channel for more journeys into real scientific research.